Okay, welcome back, everybody. So we want to continue talking about cryptography, right? Last thing that we discussed was basically, so we started with saying that we will have either public key cryptography or private key, right? We mainly focused on public key, public key or private key, or asymmetric and symmetric. And we mainly talked about the symmetric one, the private key, basically encryption mechanism. We said that essentially there is one key that is shared between two parties, the sender and receiver, Alice and Bob, or whatever you want to call them. And the goal is basically using this key and everything else open and public. We should be able to give some guarantees that only the sender and receiver should be able to decrypt this message and receive the message, right? So we start with like the requirements. We said what do we really need, and the first thing that we talked about was perfect secrecy, right? And perfect secrecy was just intuitively was this idea that if we see the ciphertext, the chances that this ciphertext is coming from any of the message in the message space should be exactly equal, right? And if you have that, we said you have perfect secrecy. Basically, we're not leaking anything about the original message. We said that achieving private secrecy requires this thing called OTP, or one-time pad. The biggest catch with one-time pad was the size of the key has to be equal to the size of the message, right? And that has, feasibility issues, practical issues it has. So we said that, okay, what can we do? And then we said that, okay, maybe this perfect secrecy was too much. Maybe we can do something better. And we introduced the concept of semantic security, right? And basically, we said that semantic security is almost similar to perfect secrecy. The difference is that we can leak a little bit, and that little bit was this epsilon number. And we said that as long as this epsilon is pretty small, for practical purposes, there is no difference between perfect secrecy and semantic security. And as I said, this could be an assumption that down the line could be something problematic, and we might need to actually make the epsilon smaller and smaller as the computers gets faster and faster. But for now, I said numbers around 1 to the power of 128 or 256 is kind of like reasonable numbers. So with semantic security, we actually can relax this and got this value that basically key can be much smaller than EM. Then the question becomes two things basically. We said that how do we expand the key, the original key, to make it a bigger key, right? And then the second thing was one-time pad to many-time pad, right? Where we want to keep encrypting something over and over, and we don't want to leak anything because we are just keep repeating something, right? So for the first one, we described the concept of pseudo-random generators, or PRGs. And we said that essentially PRGs are this algorithm that takes some seed and just expand it. And it's not just something that it's not an ad hoc algorithm. It's something that you need to think about and design it to occur. Because essentially what we want to do is that we want this final, expanded key looks very random, write a random sequence. And I said in order to achieve that, you need to run statistical tests and so on. But eventually, at the end of the day, the good thing is that there are efficient PRGs that you can just give the seed, and that can give you the key as much as the large key that you want. The second problem was, from one-time pad to many-time pad, and we basically say that essentially any deterministic algorithm has this fundamental issue. So we need to move from deterministic to probabilistic. And we introduced the concept of some initialization vector, or we call it nonce, which essentially we said that whenever we are encrypting the message, we not only encrypt the message, we also add some sort of randomness to it. And this random value should be unique for every single encryption. If we keep reusing that random value, we defeat the purpose, and basically our many-time path becomes one-time path. So we shouldn't never reuse the same random number over and over again. But the trick was make this very big enough so that we never need really to wrap around and reuse our nonce again. And the good thing about nonce was that you can just send it in clear. You don't have to be worried about the privacy or confidentiality of your nonce. You can just basically just share it, similar to the way that you share any public knowledge. Okay. So that's kind of like where we were last time. Any questions at this point about things that we discussed last time? All right. So now the last thing we said was basically stream ciphers, kind of achieve what we want, but unfortunately it's not fast enough. There are some efficient stream ciphers such as Cha-Cha and Salsa. There used to be another one called RC4, which is no longer secure because people found a way to actually break it. But generally for modern systems, in order to encrypt and decrypt quite rapidly and very fast, the idea of using stream cipher, like expanding the key and then XORing it with the message, is not the fastest option that you can. Instead, you can have this idea of what's called a block ciphers, which basically is saying that we look at the message, we divide it into blocks, usually 256-bit or 512 bits and so on. And we use this concept called pseudo-random functions, or a specific version of pseudo-random functions was pseudo-random permutations, PRPs, which PRP is basically this machine that takes whatever inputs a block and just commute it and map it to another block. All right, so it's from same domain to the same domain. So let's think about like all the numbers from 0 to the power of 256, for example. So all the possible numbers, and what it does is basically just randomly map one element to the other element in that domain. And it has to be one-to-one function because of that correctness requirements that we said that all the encryption algorithm needs to have. So basically, it's just this domain of all the possible numbers, and what the PRP does is just map this randomly to another point in the same domain, and it does it for every single element in this domain. All right. And since this is very large, and the possible amount of permutation is really large, as I said last time, it's kind of like bigger than the number of atoms in the universe. Brute forcing and searching through to finding that permutation is not possible. And as I said last time, the requirements is that the PRP should be indistinguishable from a random permutation. So essentially, if the adversary see a Q core is Q pair of these random permutations, basically the message and the ciphertext, and see Q of these, and then ask the adversary to tell me what is the Q+1 mapping. The adversary should not be able to tell that with significant probability, right? So the probability of that should be just 50% plus some epsilon. And in this way, we are basically getting the semantic security that we want. All right. Any questions at this point?
So what part of this is procedural? I mean, how do you know? How do you know like the pattern with which it was mapped into this considering?
So how do you you're asking like how do we build the PRPs or?
Yeah, like what is the you say that it's pseudo random. So what is the procedure?
We're actually going to give you an example. So there are multiple ways of implementing this. The most popular one is what's called an AES algorithm, which basically does this for us with some with some specific procedure that I'm going to actually, I think probably next slide or something. Okay. And then, as I said, basically, when we have this PRP that is secure, all we need to do is just take blocks, encrypt it, go to the next block, encrypt it, go to the next block, encrypt it, and so on and so forth. All right. And then, as I said, as long as this looks random, looks like a random sequence, we can prove that this is achieving the same amount of security as stream cipher. So basically, this is a semantically secure system. Okay, so answering your question, how do we build PRPs? All right, and building PRPs is actually kind of like a theoretical plus some engineering problem. So there is no specific algorithm that say that if you follow these steps, you're going to get a PRP. Nobody really knows how to build PRP. So basically what they do is kind of combining different, some say of ad hoc algorithm that build something that seems to be a PRP. Again, the requirements to know whether we have PRP or we don't have a PRP is running the statistical tests. And if let's say, if I'm claiming that I have this function, I have this algorithm that is actually indeed a PRP, I need to pass a list of tests in order to show that. Actually, those set of tests is a standard test developed by NIST, the National Institute of Standards, and you actually do know whether just your algorithm that you're coming up with is in actual something that looks random or not. So it's not something that you can claim or not claim. There are specific set of procedures that you can follow and then say that whether this algorithm is a PRP, at least an acceptable PRP, random, look random enough or not. All right. But generally, designing a PRP algorithm is not something trivial. So it requires years of engineering, and it's as complicated as, for example, designing sophisticated hardware. All right, and so a very long time ago, we had this thing called triple DES, which was originally we had DES, and then we had triple DES. Which basically was this PRP algorithm. Later on, people show that triple DES is not secure enough. It actually a sophisticated adversary can break this assumption that I described to you in the last slide, where essentially the adversary can tell the difference between, for example, this pattern and that pattern. All right. So it's around, I think, 2000-ish. There was another call for coming up with new PRP algorithms. And the winner, the finalist, was this Advanced Encrypted Systems, or Advanced Encrypted System, or AES, which was designed by this, I think, Dutch scientist, Rindel. So this algorithm is basically, again, has multiple different rounds, which I'm going to show you in the next slide. But what it does is, based off those set of tests that's depicted by and provided by NIST, it actually has all those tests, which means that it actually has randomness enough that we can use it for our regular encryption and decryption. And to this day, there is no known attacks to AES. All right, so there are lots of efforts in trying to break AES, but so far, at least, luckily, we haven't seen anything that actually breaks it. Right, so AES is basically the gold standard these days for any sort of thing. Okay, any questions? Okay, so how does the AES work? So AES is this thing that has a basic key. The key actually, using a key expansion algorithm, has expanded into multiple rounds. So basically, AES is this algorithm here, which I'm going to describe what it is, but it's actually done in multiple rounds. All right, so you just keep repeating the same thing over and over again until you reach a certain level of security that you're kind of done with, this is enough for the system. Specifically, AES these days use 10 rounds. So we have 10 of these. Oops. So N is basically equal to 10. Why are we using 10 and why not 9 or 11 or 12 or something like that? Again, there is no theoretical answer for it. There is an empirical answer for it, because at 10 we reached enough level of randomness that is passing the test that we need to pass. And of course, when we are reaching to that, we don't need to do more because latency is one of the big criteria for us. So the minimum number of rounds that you can achieve enough security and enough randomness, that's where we're going to stop. And for AES specifically these days, that number is 10. So we kind of like repeat it 10 times.
What exactly is each round doing?
I'm gonna describe it a little bit for you. If that's what it does.
If you have a key expansion, then you still have the problem that you have with cipher stream, or isn't it the same thing when you're expanding?
That's a great observation. The key expansion doesn't use PRG. This actually uses another clever algorithm that I'm going to describe what it is. But yeah, that's a very good observation. Any other questions? No.
I'm not sure. I'm still not clear structurally what's different about the block cipher versus the stream cipher.
So if you remember, stream cipher wasn't looked at the blocks. So X here is actually a block. It's not one bit. It's a block bit. So for example, let's say usually AES works on 256 blocks. So your X in this case is 256 bits. For stream cipher, your X was just one bit.
Okay.
And you had this machine that takes the streams of one bit, has this key expansion algorithm, and then basically just XOR this on the fly and then get the result. This XOR part was actually quite fast. The problem was this key expansion part using pseudo-random generator. So generally, as a matter of fact, PRGs are much smaller. Much more slower than PRPs. All right, so that's the problem that we have. That if you want to create a pseudo-random generator, creating that, at least the known algorithms that we have so far are much less efficient than the PRP algorithm that we have. All right, so that's the reason that stream ciphers are not as great as block ciphers. Okay. So yeah, a few notes here. So first of all, if you just use one of these blocks only one time or two times or three times, you're not going to get the security of the requirements for NES. This actually is important to have exactly the same amount of rounds as described by the algorithm. Again, we don't really know why we have like 10 or why not 9 or 8. But again, if you maybe read a little bit about AES, you get some explanation. But generally, as I said, there is no theoretical work on why we have this number of rounds. And again, the number of rounds is something that you want to have as small as possible. So ideally, if this was just only one round, we would have been much more happier, because essentially the encryption takes 10th of what we have right now. But still, this is fast enough and that we are happy. Okay. The important things that you always have to remember is that essentially for PRP, you need to have some nonlinearity. If your system is completely linear, which means that if you just add and multiply in any random fashion, you're never going to get randomness that you want. The adversary can always reverse engineer your system and find it. So you need some sort of nonlinearity in your each round, otherwise the system never gonna look random. All right. So this is kind of like this is the same thing that happens for every single known algorithm that we have that has been used for security for encryption. And it has to have at least one random component in each of the rounds, one nonlinear component in each of the rounds. All right. As I said, speed is the major criterion in all of these. And so you ask what is going on in each round. To understand exactly what is going on in each round, I highly encourage you to just Google and see what's inside the AES. But basically, each round has three main components: what's called a subbytes, a shift rows, and mixed color. The subbytes is actually the nonlinear part. So it's a very interesting thing that's kind of like basically what it does is mix and match some of the bytes. So it kind of move bytes into different directions. There is this network called pi-cell network, which actually used originally in DES and triple DES, and then we use in AES. So what it does is kind of like, just moving around some of the bytes within the 256 bits that we have. And then the shift rows and mix column is basically taking out again some of the bytes and moving to another direction and another direction.
I don't understand what you exactly mean by linear and nonlinear.
So I mean, linear and nonlinear, we mean the operations that you do on data. So basically, if you do addition and multiplication, that's linear operations. Things like if and else, generally nonlinear functions versus linear functions, the mathematical definitions for it. So remember, at the end of the day, what you want to do is permutation, right? So you want to kind of like, move things around until you get a new permutation. And AES is basically each round of AES, that's what exactly we are doing. And again, we're not, just adding and multiplying, we're actually moving things around to create that nonlinearity for us. All right. So again, look through, how exactly each run does. It's actually, there are like nice pictures and so on. We don't have time to go through it, but it's very clear what they do. Now you know that what's going on with the original. You have the big picture, so you should be able to understand how it works. Okay. Okay. So a bunch of questions about AES and generally any other block ciphers. The first question you already asked, that how do we do the key expansion? Because we generally said that in stream cipher, the problem that we have is the key expansion part, and it seems that we have the same problem here as well. So how do we fix this problem in order to get the speed that we want? The second two questions kind of relevant to each other, and we kind of fix it all together. The first one is basically if we have much more than one block, like if we have multiple blocks, what do we do? Do we just take one block and encrypt it and go to the next block, or is it kind of chaining going on between multiple blocks? And then finally, remember, we always need randomness in this process, right? So if we have a message and then we feed it to the block cipher and gets the encrypted message, the next time that we are feeding the same message to the block cipher, we should get the different results. Otherwise, you're going to have the same problem with OTP, which basically the attacker can do frequency analysis on our encryption. So we need definitely some sort of randomness. Okay. So let's see how do we fix this too. Let's focus on the first one first. So the idea of key expansion is using something called pseudo-random functions. Pseudo-random functions are very similar to pseudo-random permutations. The only difference is that when we are doing the mapping, we're not mapping from same domain to the same domain. We're actually mapping from X to another domain Y. Again, the mapping has to be one-to-one, but we are just from one domain, we are mapping it to another domain. All right. So that's the biggest difference between pseudo-random functions and root pseudo-random permutations. And based on this definition, basically pseudo-random permutations becomes a subset of pseudo-random functions, right? Basically, if X is equal to Y, our pseudo-random functions become a pseudo-random permutation. If X and Y are not equal, then we have a pseudo-random function. We have a PRF instead of PRP. All right. Again, same situation with pseudo-random function is that it has to be indistinguishable from a random function. So we shouldn't be able to tell which function we have used. And the beauty of this pseudo-random function is that, again, there are very efficient algorithms to create pseudo-random functions. And what you can do with pseudo-random functions, one of the key use cases for the pseudo-random functions is actually creating PRG off of pseudo-random functions. How? You basically all you need to do is basically if you have a K, so remember the PRG was an algorithm like this. It takes K, it takes a seed and expands it, right? So you can replace this G with this pseudo-random function, and all you need to do is just changing the inputs multiple times. So you use the key as before, we just use a different value each time that we call that function. And this results in different values. We combine them together and we have the expanded key that we have. All right. And these x's can be just random numbers, or it could be a counter starting from 0 all the way to whatever number of expansion that we have. So for example, if we want to expand it 10 times, we call this function with different inputs 10 times, and we get the value that we want. All right?
What's an example? What are the domains? What makes a domain different?
So for example, let's say we have values between 0 to 200, 128 minus 1. This is one domain, and then the other domain is 200 to 128 all the way to 256 minus 1. So from one domain, we are mapping it. So from smaller than 128, we map it to the bigger ones.
Could you repeat how we create PRTs from PRFs, like the last one? The function?
Yeah. So think about that. We have this function that creates outputs for us, right? And this function, it looks random. So what we do is basically we just call this function multiple times with different inputs. And each time it creates a different outputs for us. Okay? And then we just concatenate these outputs in order to create the expanded key for us. Okay? And again, the key thing is that calling this function multiple times is much more faster than having an original PRG such as cha-cha or salsa and so on. That's the reason that we prefer to have a PRF and call it multiple times rather than using a PRG.
So I don't think different inputs from X1 to XL.
No, these are just different. You can think about it as different random numbers that we feed into our function. So this is just an example for maybe I'll call it y1, y2, and yl, and then makes it easier to understand. So what we have, remember here, we have a key and we want to expand this key into multiple keys because we want to use it for multiple rounds. So for example, in this case, as I said, n is equal to 10. So basically we want to expand the key 10 times. What we do is that we have a function that gets the k, and then we can call it fk1, k2, and so on and so forth, 10 times. So basically all the way to 9. And that gives us k1, k2, k3, all the way to k. And then we're going to use that in each round. So each round I'm going to use a different key. Okay? And this is actually a PRF. It's not a pseudo-random generator. So it's not a PRG. It's not a PRG because PRG is not fast enough. Does it make sense? Any other question?
So what exactly is the PRG doing that makes it slower than the PRF?
It's just the way that we design PRG. So again, you have to go and look into how we create pseudo-random generators and how we achieve the randomness that we want that we cannot really do with the actual PRGs. Again, these are not, so there could be a very efficient PRG that we could have used and much more faster than PRF. Right now, we don't have answer to it, unfortunately. Does it make sense?
So if this is the case, then that means that your key extension function needs to be known to parties.
Yeah.
And that's all right.
That's all right, because key is secret. So again, PRF, you know how PRF works, but you don't know the C. And that can give you semantic security because it looks random. So nobody knows how, even seeing the patterns and knowing the algorithm, you don't know what exactly would be the input. So if you don't know the key, you cannot tell what's going to be K1, K2, K3, even though you know the algorithm.
Does that mean that the function of the PRF needs to be nonlinear?
It is nonlinear and it's also a keyed function. So you need K. You need K as the input as well. So it's not just X1, X2, X3. K is also part of the input. So it's a keyed function. So if you don't have the key, so there is actually a proof for this, that if you have F and if you know X, But if you don't know K, you cannot tell what the output of this function is.
Where did the XLEs come from?
You can generate it randomly on the fly. So again, zero, so similar to nuts.
You have to like send it with your encryption or whatever,
So both the encryption and decryption needs to know exactly what those values are. You can start with some counter or you can send it over. Any other questions? Okay, so we kind of fixed the first problem. We know how to do expanded key. We just need a pseudo-random functions. Again, how we implement pseudo-random functions and PRP and PRGs is something that is a homework for you guys to go and look at it. But it just give you the intuition of what they're trying to do. So now let's look at these two other problems that we want to actually encrypt multiple messages, multiple blocks. How should we go about that? So the easiest thing that comes to mind is, okay, what we can do is that, okay, divide the message into the blocks, just treat them separately and encrypt each one separately, right? And this is usually called electronic codebook or ECB method. And it's actually a very, very bad idea. And the reason for being a very bad idea is that it basically, if there is some sort of a bias in your message, you're gonna see that same bias in your encryption. If you actually search for ECB, there's a very famous picture of this kind of like a panda that originally, not sure if you can imagine this is a panda. So if the original message looks like this, if I encrypt this, I'm gonna get something that looks different, but you're gonna actually see the pattern of panda in the encrypted message as well. And the reason for that is I just took out each message separately and then encrypted. And if there is a bias, potentially there will be a bias in your ciphertext as well, right? So this is not a good idea for encrypting a message that is more than one block. What should we do? There are actually multiple solutions for it. I'm going to just describe one of them to you. There are two main ones that usually use a lot. There's one called counter mode or CTR mode, which is basically the one that I'm describing the algorithm here. Another one called chaining block one, which is called CBC. So you either use CTR or CBC, but there are multiple others. Again, if you're interested, if you read the reference book, you will see the difference. So what is the CTR, which I'm gonna show it here. Basically, the algorithm is we want to encrypt something, and we have a message that has multiple blocks. So for example, a message that has R different blocks. And what happens is that all the messages are n bits, except the last message might be less than n bits, right? So you never get perfect size for all the messages. So all the others, you basically divide the message into n bits, and n bits is basically the size of the inputs for your AES. For example, imagine that n is equal to 256, right? So first question, what would happen if your last message is not n bits? We usually pad it with zeros, all right? So it's actually safe to usually pad it with some zeros. So the last one we can always pad. Then what we do, we start with some random values as nonce or initialization vector. We usually call it IB or initialization vector. And then we're gonna basically just put the initialization vector in our first block of ciphertext. So C0 is just the initialization vector. Then we're gonna repeatedly, start encrypting. But the encryption is not just a simple encryption that we just take MI, feed it to our encryption and get CI. We actually do the trick like this, and I have the picture here. Maybe this is easier to understand. So we start with nonce, and we start with using some counter CI or call it counter. Initially, we're going to start with 0, and then nonce, as I said, is just a random value, right? So what we're going to do is that we're going to first do nonce plus the counter, the IB plus the counter, and using our key, we're going to just encrypt this value, all right? Then we're going to XOR this value with our plain text, the first block of our plain text. So in this case, M0. When we get our M0 with this encrypted message, we get our C1. Okay. And then we keep repeating this. Next time, we're going to just encrypt the counter by 1. We have the same nonce as before. The nonce doesn't change. Now we're going to add this together. So this is a different number than this. We're going to encrypt this with the key. And now this is basically M1. We're going to XOR this, and here we're going to get C2. Remember, C0 was our nonce, or IB. Okay? And then we're going to keep repeating this for all the R different blocks. Okay? So we're not directly feed this into our block cipher encryption and get the results. With this trick that we start with some nonce and with some counter, we encrypt that and we XOR that with our plain text. And that's the difference between what we normally get from ECB and for a method like CTR. Okay? And the key thing here is that this nonce has to be set. So each time we are encrypting a message, all we need to change is basically this nonce. And we have to make sure that we use this nonce only once. And since we are basically sending nonce as C0, all we need to send out to the receiver side is basically the entire C vector, which the C0 part would be the nonce. So the receiver gets C0, and that would be equal to the nonce. So that's how the receiver knows what the nonce is. The receiver also starts his or her counter with all zeros. And then all it does is, again, doing the exact same thing that we are doing on the transmitter side. So we add these two together. We use the same key. We encrypt it again, which is in this case basically the decryption. We use the exact same algorithm. This time we XOR this value with our ciphertext, and the results will be the plain. Okay. And the reason for this that we're going to get the same results, again, you can basically drive the math. You're going to see that if you XOR something twice with its own, you get the original message. And then we're going to keep repeating for all the other blocks. So we're going to increment the counter by 1. We already have the same nonce, encrypted, XOR it with second block. Basically, this one was C1. This is going to be C2. So this one going to be M0, this is going to be M1, and so on and so forth. Okay? So this is our counter mode AES encryption, or generally counter mode block cipher encryption.
It's the same nonce per block. Each block.
Yeah. Each block you get the same nonce, but basically the trick is each block gets a different input because we are incrementing the counter. Right? So for each block, we are encrypting something different. So nonce plus the counter.
Just to clarify, how you get the same plain text again? You're saying that the ciphertext is initially the encryption XOR with the plain text.
Mm-hmm.
So then when you XOR that with the encryption again, that cancels out and you get the plain text.
Mm. We're good? So this is just the algorithm, just what I just described. So if you want to see how the algorithm works, so the encryption gets the IB, which is the nonce, plus the I was our counter. It takes the key, the actual key, and then we get the PI. So basically this was PI. And then MI XOR with PI gave us the CI. All right, and then we can just keep repeating this over and over for all the blocks. And this actually can be proven that this has enough randomness that we want. Okay.
Since all these operations are individual, in practice, is CTR mode ever parallelized to make it faster?
You can make it parallelized, right? So you basically, as soon as you get the nonce, you can just create the counters, all the counters all at once, and then parallelize them. Yes. And that's why it's very fast, basically. The block cipher is very fast because you can do all at once. So you can do multiple, so at the block level, you have parallelization, right? Because you're not doing individual bits. And then at the block level, at the algorithm level, you also get parallelization because you run this blocks all in parallel. In fact, if you're into it, you'll see that actually Intel, for example, the Intel processors have specific instructions for AES that actually do this parallelization for you. So that's why it's really fast to block a really long message. Okay, so some few notes. So basically, the trick that we're using is if you're looking at this part here, this whole thing can be a random value, right? You can, instead of using the counter, you can just use a different random value for each of the blocks and basically send that to the receiver and get the exact same functionality and exact same security. What we usually do, which is much more easier in order to reduce the amount of communication, we just use this nonce and use the counter. So basically, the initialization vector has two parts: the counter, which usually starts at 0, and the nonce part, which is random. So our vector, our inputs to our encryption mechanism has two parts: one part that is not random, and the other part that is random. And again, there is proof that this actually doesn't diminish the security of the system or the randomness system. And the very important things that I already mentioned is that then you have to make sure that the nonce part hasn't been used more than once. All right. So if you use your nonce more than one time, then there is no guarantee that the system is secure. Okay. And as a result, you want your nonce to be big enough so that you never reach into the problems of, oh, you ran out of the nonce and you don't know what to do. Okay. But on the other hand, you don't want the nonce to be too big because then your block cipher has to be also bigger, and it's going to be much more slower to encrypt them.
How do you keep track of whether we use it? You have to like keep a list or something?
So usually it's so there are ways of doing it. So usually there is some internal counters when we are creating a session. So for that you need to understand what is like a session between two. So usually when you start a network connection between two parties, you start a session and you start from 0 from there. And then basically inside the session, you kind of keep track of what you use for the messages. And when you close the connection, you basically just completely close this off. Next time you create a new session, you basically use a different set of keys and different things. Okay.
So is the lifetime of this encryption just when you want to like send a message and then you just throw the nonce out? Like, do we store? I mean, I guess that the question is kind of asked already, but like, do we store the nonce anywhere?
No. Okay. So the next time that you want to start the communication, you have to start with a new set of keys and new set of nonce. We actually, once we talk about the asymmetric one, you're going to see how do we do the new set of keys. Okay. And as I said, the last thing I already mentioned this as well, that you need to pad if your last block is not n bits, you can pad it with zeros to get that n bits. Okay. And as I said, there are other methods, including CBC, which is kind of like chaining these blocks together instead of like using a counter. That one is also pretty quick and very efficient. Just don't go over it, but if you're interested, go and check it out. There are also other methods as well, each of which, I mean, generally the difference is in terms of the implementation and in terms of performance. All right. So the reason that you're kind of like using these different methods is just getting a better performance for specific implementation. Okay, so that's kind of it for the block ciphers. So we're kind of like done with our asymmetric mechanisms. As I said, block ciphers is usually the gold standard these days for creating encryption mechanism using symmetric. So we are assuming that some way we found a way to share the keys from the receiver and the sender, and then based on that we can basically build a system. Basically. Okay. So now let's move to the asymmetric scenarios and see how do we do asymmetric? What are the main differences? But the first question is, why do we need asymmetric? What's the difference and what's the motivation of having an asymmetric encryption mechanism rather than symmetric? So the first thing to understand why we need asymmetric and why is asymmetric in some cases better than symmetric is that, remember, when we had symmetric encryption such as AES, we said that basically the plain text takes the key to do the encryption and we get the ciphertext. For decryption, we're going to use the exact same key for decrypting the message. The biggest difference between asymmetric and symmetric is that in asymmetric, for encryption, you use this thing called public key, but for decryption, you use a separate key called private. So basically, encryption and decryption does not use the same key. All right. So why this would be something interesting? Because the good thing about this is that in order to send and receive messages between multiple parties, we no longer need to agree on the same key. We don't need to find a way of sending my key to yours in a secure fashion, because the idea is that the key has to be kept secure, right? This way, all I can do is I will make this public so everybody knows what this is, and I'm going to keep this private, all right? And everybody going to do the same thing. So everyone going to create a set of keys for themselves, a public and private, and just tell the world what their public key is, all right? So in that case, if somebody wants to send a message to me, they have to use my public key in order to encrypt the message. They can send it to me, but the guarantee is that I'm the only one who are able to decrypt the message, all right? So basically, if I encrypt something using asymmetric keys, I'm going to use the public key and the message, and then I'm going to get the ciphertext. So anybody else who sees the ciphertext, even though that they know what the public key is, they cannot decrypt this message and get that. All right? Only me, who has the private key, can take this message and know what the end is. All right? So that's the biggest difference between symmetric and asymmetric. And the good thing about this is that if you want to send something to me, you don't need to contact me beforehand and find a key between us. You can just look up what is my public key is. Just send a message, encrypt the message using the public key, send it over, and it's guaranteed that I'm the only one who's gonna see that message. Right? And then the good thing about this is that with this, functionality, we're gonna get the same correctness requirements and same correctness actually criteria, and then we're gonna get the same security guarantee. So basically, it can be shown that if you follow the correct way of creating asymmetric mechanisms, we're gonna get the same semantic security. All right? But also remember that we want to have the same correctness requirements. So if we encrypt something and decrypt it again, we should get the same message. And asymmetric has to follow the same requirements as well. And again, if you want to have homomorphism, if you remember, homomorphism was when we apply a function to the plain text and apply the same function to the ciphertext. If you want to have a homomorphism, we can have homomorphism on public key encryption mechanisms. So now that I described what is the difference between symmetric and asymmetric, there is an additional attack that can happen in asymmetric mechanism, and that's what's called a Trojan ciphertext attack. So remember, we said that on symmetric mechanisms, what we need to have is CPA secure, which was Trojan plaintext attacks. And basically what Trojan plaintext attack said was, I can pick my own message, let's say message 1, 2, 3, and so on, and query the model in order to get C1, C2, C3, and so on. So I'm going to get pair of M1 and C1s, a finite list of M1 and C1s, but these M1s I can pick myself. So I can choose what plaintext I can get. And we said that generally we want our encryption mechanism to be secure against CPA. All right, so AES, for example, is the CPA secure mechanism. For asymmetric, not only we have CPA security, but we also need to have what is called a CCA security, closed ciphertext. Why? Because essentially, not only I can choose what my message is, I can even choose the desired ciphertext. Why? Because I know how to encrypt the mechanism. So, so it's not just, I get M1 and C1. I can also actively say that, okay, this C2, is created by this M2. Because I'm the one who is encrypting things. I'm, as an adversary, has access to the public key. So I can actually choose what the ciphertext looks like, because I can basically infinitely, encrypt messages and ciphertext and get any ciphertext that I want. So basically, this means that I can pick what ciphertext the victim, which is in this case is the decryptor or the receiver, is going to decrypt. All right. And this is important because, for example, I can do things like this. So for example, I can change the messages, for example, from yes and no. I can know that what is C2 is and what is C1 is. And instead of sending C1, I can pick and choose sending C2. I can choose what ciphertext I want to send to the receiver, right? And this way, so I can basically pick my message, pick my ciphertext, send it over, and fool the systems thinks that this is a different message, right? And the system has to be secure against this as well, compared to when we have only a chosen place. Okay. Okay. So now we need the requirements. Let's see how we build a public key crypto system. Before that, let's actually have maybe a 5-minute break, and then I'm going to describe to you how do we achieve an asymmetric system, encryption system. Okay. So we kind of know now why we need asymmetric, why asymmetric would be an exciting choice in some cases, because essentially all the key exchange and agreeing on the same key would be gone with asymmetric one. So asymmetric one is an interesting choice. So how do we actually implement asymmetric? The trick for that, we need, basically, if you think about it, we need what's called a one-way function, which is very easy to compute, but it's very, very difficult to reverse. Why do we need that? Remember, we said that we're going to have a set of keys, right? A public key and a secret key. And what we want to do is that this public key is going to be known to everybody. And the function that you're going to use for encryption, the E function, is also known to everybody. So it's not like NES, which the key for encryption was not known. The key for encryption is known this time. And the only thing that is not known, obviously, is the message itself. So we need a function that, if we do the public key and the message, very efficiently can give us C. But if we have C and the public key, we cannot inverse this function and get M. Okay? So this should be very easy to compute, but this should be very, very hard to compute. So we cannot easily invert this function and get the results. All right? So that's what we need. And how we can achieve this is actually very, very interesting mathematical functions called trapdoor functions. And this is actually one of the very, very important achievements in 20th century in terms of theory of computation, which a bunch of different people kind of find it. That the ones that very famous is called RSA, Reverse, Shamir, and Adelman. These are 3 professors at MIT which come up with this trapdoor function. All right. So what is a trapdoor function? So mathematical definition of the trapdoor function. So trapdoor function, or T, is basically defined over a domain of X and Y. So the inputs are in domain X and the outputs in domain Y. And basically a set of 3 algorithms. It's not just one algorithm, it's a set of 3 algorithms, right? The algorithm G is a probabilistic key generation algorithm. What it does is basically just at random sample from the domain of K, it just a random sample and creates a pair of keys, the secret key and the public key, right? And this is not something that we just randomly pick those two. It's actually an algorithm for selecting those two pairs. So those two numbers kind of like have some related relationship between each other. All right. And so that would be creating the private key and or secret key and the public key. Okay. The second thing is the f function, which is a deterministic function that takes the public key and the x and generate y, which is the ciphertext in this case. Okay. And finally, I is again a deterministic algorithm that takes y and this time the secret key and gives you x. Okay. And again, these functions has to be one-to-one, kind of like these are actually a permutation functions. Otherwise, you don't get the correctness requirement. So if you do I of f, then you should get your x, right? So if you encrypt and then decrypt, or if you send x with the public key to f, and then get the results out of that, and then send it to I with the secret key, you should get your x back. Otherwise, your encryption mechanism won't work, right? So we call this a one-way function, basically. So f should be a one-way function, because if somebody can invert f, they can easily find what x is. So they have y, they have the public key. If they can invert f, they easily can get x. So the entire encryption mechanism is full. But the nice thing is that if you have the secret key, then you should be able to invert f very easily, and then get your x back. So that's the trick here. That if you have the knowledge of secret key, you can easily invert f. But if you don't have the knowledge of secret key, you should not be able to invert f. Okay. So that's what the trapdoor function is. Any questions here? Am I recording? Yes. So how to prove that this is actually a secure function? The interesting thing about the trapdoor functions is that you can actually show that in order to solve this problem, which is inverting f, what will happen is that this problem reduced to some hard problem. For example, in case of RSA, it becomes a factorization problem. So if you have a large number and if you want to find the prime factors of this number, it's actually can be shown in computer algorithms that this is a hard problem. This is an NP problem, right? So if you cannot really, if you have a really large number, we cannot find the prime factor of that number. And what happens is that this RSA trapdoor function reduced to that. So basically it's saying that without the knowledge of the secret key, inverting the RSA function is as hard as solving this factorization problem. And since we cannot solve the factorization problem, at least there's no known algorithm for solving the factorization problem, we cannot invert the RSA trapdoor function. Hence, our encryption mechanism is secure. Okay. There's another one called Diffie-Hellman, which basically is based off what's called a discrete logarithm problem. Again, that one is also reduced to factorization problem, and the factorization problem reduced is already known as it's a hard problem. Okay. And there's a bunch of others, including what's called elliptic curve problem, ECC problem. That's also another way of public key encryption. That's also very popular and used a lot. That one is also another hard problem that you can use. There's another one that these days are actually getting more and more interesting, and that's based on lattices. And so basically, the trapdoor function is basically a lattice function. And that one reduced to usually a closest vector problem, which is another problem that's very probably most of you have seen in your algorithm class. It's usually what's been taught in algorithm class, finding the closest vector to a specific point in lattice. It's not important to know these things. It's for those of you who are interested in the theory part of it. But just know that there are a class of problems that we can achieve a trapdoor function. What is a trapdoor function? Is this function? Why do we need a trapdoor function? Because we want to be able to encrypt using a public key, but not being able to decrypt if we don't have the secret. And people have shown that this, in order to achieve this capability, this feature, we need a trapdoor function, and people actually prove that RSA, for example, is very good candidate for this. They show that the RSA actually reduced to some known hard problems. And since we don't have answer to those hard problems, we don't have answer to RSA. And so RSA is secure. Okay. So how do we use RSA encryption, for example? So just giving you an example here. So let's say we have two users, Alice and Bob. Alice is the receiver. So what she does is she uses the RSA trapdoor function for generating her public key and secret key. Remember, we had this generator function. She's going to share her public key with the outside world, including the sender Bob. Bob's going to use the RSA trapdoor function F. She's going to use Alice's public key and encrypt the message. So she's going to use F public key and the message. So this is the message that Bob wants to send to Alice. Alice then going to use her secret key. And since she knows the inverse, everybody knows the inverse function, but without the secret key, they cannot use it. So Alice is the only one who can actually takes the inverse function and use the secret key. And she's going to decrypt the message and get the message out. And again, the security of this coming from this fact that Alice is the only one who has the secret key. And Alice is the only one who can basically correctly compute the inverse function of F and get the message. Any questions? Great. So there are some considerations for this, which you don't need to be bothered with, but generally, the message should be in order for this system to be secure, the message should be uniformly distributed. So if you use a messages, that is only from a certain distribution is not uniformly distributed, it can be shown that the RSA mechanism is not secure. The trick usually is that we usually first map the message into another uniform distribution. We usually use a hash function for that to map the message domain to another domain that is actually uniformly distributed, and then use that as the inputs of our RSA algorithm. All right. So there's kind of like one mini steps between actually doing the encryption. And the reason for that is that we want the input of our RSA algorithm to be uniformly distributed. There's a mathematical reason for it. We're not going to talk about it. The encryption has to be randomized. So again, what we do is that we usually, when we're doing this mapping, we also add similar, IB that we do with the symmetric encryption. And the final thing that is kind of like the biggest challenge with asymmetric encryption mechanism is that we want to be as efficient as possible. Remember, the whole point of, for example, using block cipher instead of stream cipher was that the time it takes for encryption and decryption has to be very, very small, right? And unfortunately, for asymmetric encryption, that this is the biggest downside. Encryption and decryption in asymmetric mechanisms, unfortunately, is not as quick as a system like AES. All right. So it takes actually 100 times or more compared to AES. So you really, really want to use AES if you can, because it's much, much more faster than something like RSA. But on the other hand, you cannot really use AES if you don't have the key shared between the users, right? So the trick to kind of like have the best of both worlds is this concept called hybrid encryption, which what we do is that at the beginning we use asymmetric encryption to just send out the key. And once we send out the key, then we can use asymmetric encryption. How do we do it? Basically, this is the algorithm. So this one is RSA. Okay. So what we do is that we have the public key, right? And we have and instead of actually sending the original message, let's say we want to send M from Alice to Bob. Okay. Instead of sending M, what we do is that we create an AES key and call it key. Okay. Instead of sending the message, I'm going to encrypt K using an RSA algorithm. So I'm going to use the public key. I'm going to use RSA encryption algorithm. And instead of encrypting the message, I'm going to encrypt the key K and use C. Then Bob gonna decrypt this message using his secret key. And what he is gonna get is the key. Okay, the K, right? Because you're basically encrypting the K, sending it to Bob. Bob gonna decrypt it and gonna get K. And now this is the trick that we use. So now both Alice and Bob has access to this AES encryption key, right? So now what we're gonna do is this time I'm gonna, instead of encryption doing the sending the message using RSA, I'm just gonna encrypt this message using AES. So this encryption prime is actually AES. And I'm gonna use the same key that I sent before and encrypt this and send C prime. This time, Bob gonna decrypt this, but we're gonna decrypt this using the AES key. And he's gonna get the message. All right. So what happened here is that it's similar AES encryption mechanism that I just described in past few slides, but the assumption here is that we originally didn't have access to the key, right? The receiver didn't have access to the AES key. So we first use a round of public key encryption to send out that key to Bob. And then once Bob has access to the key, then we can just continue regularly with our AES system. And this is very efficient because essentially in the whole communication, we never actually agreed on a specific key, right? Because we used a public key at first, and public key was the general knowledge. Then we use that in order to send the information to Bob. Bob now has access to the key, and then we can continue with our AES encryption. So only one round of RSA, and the rest is AES. And the reason that you're doing is that AES is much more faster, much more lightweight, and much more easier to implement than RSA. Okay? Good?
Before, in asymmetric encryption, it's mentioned that the message should be uniformly distributed. How can we guarantee that we're just passing in like something that we wrote, for instance?
So here the requirements is key has to be uniformly distributed, which is generally is the requirement for AES key anyway. So this is okay. And the second part is for the AES. So AES does not have that requirement, so we're good. So here, the key has to be uniformly distributed, and that's already a requirement for AES keys. You want the AES keys to be uniformly distributed. If you go back at the beginning of my slides, you saw that in order to achieve perfect secrecy, you want the key to be uniformly distributed.
Was that a type of it in the previous slide? It says the message should be uniform.
So we are talking about RSA. So generally, the message for the RSA, the input to the RSA has to be uniformly distributed. In this case, K has to be uniformly distributed because K is the message for the RSA. What I'm saying is that the K is generally uniformly distributed anyway, because that's the key that we generate for AES. If it's not, as I said, the trick is usually send this to another mapping function, which usually a hash function, which I'm gonna in a few slides I'm gonna describe what it is, and then get a K prime and then send that to RSA. So this mapping, making sure that this is now uniformly distributed.
How often do we update the key? Right? if we want to start a new session.
Any new session, remember I said that for any new session, we need to throw away the key and start with a new key. That's exactly what we do. Okay. So that's kind of the end for our encryption mechanism, decryption mechanism. So RSA and AES are two main ones that these days being used. RSA is much more convenient in terms of we don't need to agree on a key, but much more slower than a symmetric encryption mechanism like AES. So as a result, we kind of like always do the combination of these two together, right? So you typically use a hybrid encryption mechanism. Okay, so now let's talk about the other primitives in cryptography. Mainly, we're going to talk about hash functions. We're going to talk about message authentication codes or MACs, and we're going to talk about digital signatures. All right. So let's first talk about MACs or message integrity. Why do we need MAC? Remember, I said that generally three things that you really care about, right? Confidentiality, integrity, and availability. With encryption, you're going to get the confidentiality, but AES or RSA does not guarantee integrity. So for example, if I change things along the way, so if let's say I send a ciphertext and there's an attacker who changed the ciphertext and created C prime, and then send it to the receiver has no idea that this ciphertext has been changed. Specifically, if this ciphertext is actually a valid ciphertext, the attacker is gonna encrypt this and got M prime, okay? And then thought that the message that has been received has been sent is actually M prime, okay? But this is actually for emails. This is the very common type of attacks where all your emails is essentially encrypted. But what can happen is that in a malicious network can just mismatch and mix and match your emails together and send another email to another user. All right. It can change the receiver, it can change the content of your message and so on. So it doesn't change your content, but it actually replaces it with something else. All right. So in all those cases, you need integrity of the message to be also guaranteed. And that's where this message integrity code is coming from. So basically, we want to make sure that if Alice is encrypting a message M and sending the message to Bob, Bob needs a guarantee that this message has been the ones that Alice was intended to send. How do we achieve that? Basically, we're achieving that with adding this additional tag to our message. So we not only send the message, we also send a tag with it, which usually the size of the tag is much smaller than the message. But if we send this tag, what all we need to do is that basically checking whether this tag is generated by this message or not. So here's the protocol. Alice has a message M. She's going to use a function called G or generator algorithm and creates this tag, right? Then she's going to send this tag along with the message, and Bob's going to get the message and going to get the tag. He's going to compute the tag for itself. So he's going to use a verifier algorithm that takes M as an input and create the tag. He's going to compare this tag with this tag that's been sent with the message. And if these two agrees, it means that the message has not been made compromised, right? If the tag has been changed, it means that either the tag has been compromised or the message has been something else, and now it's done. Okay, so this is the idea of the message integrity. I'm sure that you're now kind of thinking, well, okay, how the attacker can be convinced of this, and there are multiple things that the attacker can do. Anybody has any idea what the attacker can do with this network? And essentially, what is a secure map? Cynthia? That's one way of doing it, yes. So you can generate a different tag, yes. Any other ideas? What's that? Replay attacks, exactly, right? So you can just send the same message over again. You see the tag for that message. The next time you just send the same tag and the same message. right? So two things that we can do. One is what's called a forgery attack. So what we are saying is that basically a secure message integrity or secure MAC should be able to protect itself against forgery attacks. So essentially, we should not be able to create any valid message and tags if we don't have that secret value. So first of all, message integrity also use a secret key, and the secret key is only known between Alice and Bob. So if the secret key is known to the other people, then the message integrity is no longer secure. But what we are saying here is that if we don't have access to the secret key, or even though we have access to the verifier and generator algorithms, but we don't have access to the secret key, we should not be able to create any sort of valid message and tags. All right. And then this kind of like when we are saying not any valid message, this is kind of also automatically guaranteeing these two things. That if we see a message, we should not be able to tell what is the correct tag or valid tag for this. Or on the other hand, if you see the tag, we should not be able to tell what is the correct message for this, right? So we should not be able to tell any of these. No to valid message and tags. And the results, if you see a message, we should not be able to say what is the correct tag for this. If we see a tag, we should not be able to say what is the correct message for this, unless we have access to the secret. Okay? So that's the forgery attacks. The second thing that you mentioned was replay attacks, right? So even though that we cannot generate this, of course we can see this, right? So we can see that, for example, somebody sends a message, and along with that message, send this tag, okay? So at least we're going to know that this is a valid tag for this valid message. The next time the attacker sends M2 with T2, the sender sends this, what we can do, we can just discard this and send this instead, right? So again, I can exchange messages if I want to. And that's going to be another problem. So for example, I say yes, but what the attacker does is that just exchanging my yes to no. And since I already said no, maybe a few steps before, knows what the correct tag for the no answer is, right? So what should we do for this? We basically need to add similar way that we did for encryption. We need to add randomness or nonce for each pair. So basically, our message is not just a message; it's a message plus some nonce. And we basically compute the tag for this. And the second time I send the exact same message, the message is the same, but the nonce is not the same. So the tag would be different. So in other words, I never use the same message tag ever again. I only send it once. The next time I want to send the exact same message, I'm using another nonce and basically another message in some sense. And I'm going to compute the tag over that. Does it make sense? Anybody has any questions? Cool. So how do we get secure MAC? We already have lots of tools already, so we can quickly go over that how we can create this. One easy thing to do is, remember I said pseudo-random functions has many different applications. One of the key applications could be generating the MACs for us. So basically all we need to do is we need to pass on the message and the key and call this function and get the output of that, and that would be the tag that we call. Okay. And again, as I said, this message is basically the actual message. So maybe we call it M prime. M prime is basically M plus some nonce. All right. And the idea is that, you know, both sender and receiver has access to the PRF. PRF is basically known to everyone. It's a public knowledge. But what the attacker does not have access to is this key. So without this key, we already proved that how would be possible for the attacker to compute this tag. Okay. And again, since this is similar, the security of this is similar to AES, if somebody sees the tag without the key, cannot say what the message is. If somebody sees the message without the key, they cannot produce the tag, right? So that's how we get the security.
We use the same key of when we're encoding the message, or it's a different.
You can use the same key, yes. But usually the difference between what you use for Mac versus what you use for AES is that the size of the tag is very, very small compared to the size of the message and compared to the size of the ciphertext that you use for AES. So this is much more efficient in terms of computation. Okay, but again, the tag should be big enough that you don't see repetition of the tag. So you cannot use it like maybe a 2-bit tag. You need the tag to be large enough that eliminates any chance of a brute force. Okay. So this is kind of like now what would happen if we have a long message, similar to the way that we kind of use a counter mode. We usually use what's called an nmac or nested mac, which generally what it does is that this function is basically the function that is described here. If you have multiple messages and we want to create one tag with this big message, of course, what you can do is that generating tags for each individual message, but that's not the greatest way of doing it. What you do is that what's called this cascaded map. Okay, so you start with the key. You get the first block of the message. You compute call your pseudorandom function. You get the outputs. You send this output to the next round of your pseudorandom function. This time the input would be M1. So basically this would be the key for this round. So you're kind of like changing the key based on the previous message. And then you get your final T. There's this additional rounds that you need to do some padding with your T. The reason for it is that people have shown that if you don't do it, people can basically repeat your message and eventually figure out what your key was. There is a mathematical proof for it, which we're not going to go through. But just remember that we need to pad our final round of cascaded MAC with some constant value. Okay, so this F pad is basically a constant that we need to use in cascaded MAC. And then finally, there's going to be another round with a different set of keys. So instead of like similar to AES, but slightly different, we're not going to use the same key over and over again. We're going to use 2 sets of different keys. And again, the reason for this is we don't want to, if we repeat this message, the attacker can basically, what the attacker can do if we just send this out is the attacker can add multiple messages on top of this and basically get this number and then compute the tag for this and get the results. So instead what we do is that we encrypt it, we compute the MAC one more time with a separate key, and this time we kind of like, decorrelate what we are computing at this point with what we get as the tag. Otherwise, there's a very known attack called cascading attack, which essentially the attacker gets this tag and add another message to it, get the tag of that, add these 2 tags together, T1 and T2, and get the final tag. Okay, so it's kind of like a 2-round kind of thing.
How is this very different from CPC?
Slightly different, but kind of similar to CPC. Yes. The only difference is that you use another key for the last round. So for CBC, you don't do that. And the reason for that is, again, if I only done it at this point, so this is they use this as a tag, the attacker could have easily just concatenate 2 messages, concatenate 2 tags together, and that would be a valid tag. And that would have not been. So what we do here is that we just pass it in another round. Of course, this means that slightly more complicated key structures, because instead of 1 key, we need 2 keys. But if we figure out a way for sending 1 key, we can figure out sending another key. So that's not a big deal. Okay?
So it's not add just like another key.
No, FAT is a constant. It's like a nonce. So it's known. So everybody knows what FAT is. Are we good? The only reason that we need to do FI is basically making sure that here at this point this kind of has a uniform distribution. Okay. So that's how we create a MAC, and MAC is really important because whatever message being sent, we don't need to just encrypt it. We also need to make sure that its integrity is also not violated, right? So we usually combine max with our encryption. Two separate things, right? So we said first encrypt and then we do the max. Okay, so the second thing is hash functions. So the hash function generally, regardless of security, is any function that maps some arbitrary size data to fixed size data. So for example, if you have a list of, a database of names with first name and last name, of course, the size of this might not be the same for every single first name and last name. But what you want to do is creating some sort of a hash for this, something that is fixed size, and usually the size of the hash is much smaller than the size of the keys. Okay, and since we are mapping something in a higher dimension to a lower dimension, of course there will be collisions, right? There will be scenarios that multiple of these keys mapped into the same hash function, right? Because for example, you're mapping 1,000 things to 100 things, of course, there will be at least 10 of them that always map to the same thing, right? But that's not an issue generally. As long as our hash is kind of random enough, we should be good to go. But that's a separate story. That's what should we do with the collision and so on. But generally, that's why we use hash, and hash being extensively used in many different scenarios, not really related to security. Okay. Usually call this the jest or just simply hashes. So when we're saying the hash is this, it means that the outcome of this hash function is this. But there is a separation between what's called a secure hash and normal hash. Just remember that not all the hash functions are secure hash functions. Okay, there's a distinct definition of what is a secure hash function. And for having a secure hash function, we need a property called collision resistance. All right. So what collision resistance says is that, let's say we have a hash function that maps the domain M to the domain T. And of course, as I said, the size of the input is usually much bigger than the size of the output. When we're saying a collision, it means that for any pairs of messages, M0 and M1, the collision happens if the hash of M0 is equal to hash of M1, if M0 is not equal to M1. So for example, in the previous case, John Smith has collision with Sandra D. All right. So we said that there's a collision between this message and this message. All right. So what is the collision resistance property? We are saying that it should be, for a secure hash function, it should be very hard to find any collision in this algorithm. Okay. So generally, we say that, okay, use whatever algorithm that you want to use. We don't care. It should be very hard for you as an adversary, given this hash function, find a collision for this hash function. Okay. So that's what the collision resistance means. And if a secure hash function is indeed secure, it should have this property, the collision resistance property. Any questions? Is it clear what the collision and collision resistance is?
How is the collision resistance enforced?
So first of all, collision is unavoidable. So we're gonna get collision no matter what. What we are saying is that the probability of finding that collision should be really low. So when we are designing our hash function, which there are known secure hash function designs, the designer has to make sure that the probability of finding collision in his or her algorithm is very low.
So like there's no identical pattern to like which will.
Again, it's very similar to the way that we design AES.
Yeah.
There's no algorithm for it, but it's just a set of tests that you need to run in order to make sure that your algorithm is collision resistant. And then here, just remember that we are saying any algorithm, any efficient algorithm. By efficient here, it means a polynomial algorithm. So you can spend as much as time you want in the polynomial domain, and you should not be able to find a collision. Okay. And usually this algorithm is nothing but a brute force. So basically the attacker starts from the beginning, takes a message, and just keep trying different messages until he finds a message that has the same hash function. And we're basically saying that this probability should be very, very small because the domain for message should be really, really huge that the attacker cannot easily just brute force, right? On top of the collision resistance, actually there are two other properties that come automatically. If we satisfy collision resistance, we're going to get these two things. One is what's called a pre-image resistance, and the other one called second pre-image resistance. There are proof that actually if we have collision resistance, we're going to get these two automatically. But to just give you an idea of what is pre-image and what is second pre-image, is that we are saying that if we see a hash of a message, we should not be able to say what that message was. So if you tell me this is the hash value of your message, I should not be able to say what was that message that this is the hash function for, right? If we could tell it, we basically there are ways to show that if somebody can easily from seeing the hash say what the message was, they can actually violate the collision resistance problem. And the second pre-image is basically similar to the collision resistance, what's the weaker version. It basically says that if I see the hash of M, I cannot find another message that its hash is similar to the hash. Okay. And again, it's very similar to the collision resistance. The collision resistance says that there's no any pair that I want to choose that I can find a collision. Second pre-image says that if there is a given hash, I cannot find another message that has the same. Okay. So if I see the hash, I cannot tell what the message is. I cannot also create another hash that is same as this hash. Okay, I cannot find another message that has the same hash as this hash. All right. And final things about the hash function is that hash function is not a key function, right? So hash is just this random function that maps a domain to another domain. So there is no notion of secret key, right? And so all it does is basically just takes an input and creates an output. So we don't have a key, unlike the map. So what would be a use case of hash? There are many different use cases for hashes. One of them is actually you can use hash to create maps, right? Remember I said maps can be used using PRFs. Actually, people have found that if I use hash, it would be much more faster than PRFs. How do I create that? I create it using this kind of, again, similar to the cascade, to the nested map, but this time instead of using the F function, I'm using the H function, the hash function. And the difference is that the H it's much more faster than the F, the pseudo random function. Okay, and there are slightly different things as well, including that I need to begin the hash function with some sort of initialization vector and some padding. And remember, since we are using the MAC, we have the notion of the key. Okay, so this is the key that we use for MAC. So we initially kind of compute the hash function of the key with some initialization vector. Then we're going to use this new key with this M to create another hash and another hash and another hash and so on. And we finally get the tag out of this. Remember, this part was similar to the nested MAC. Remember, I said there are two different keys. So here's the first key and here's the second. Okay, so very similar to the nested MAC. All we did was basically replacing the F function with the hash function. And we get lots and lots of more performance out of this. All right, so final things, and I'll let you go. There is this notion of authentication encryption. And what is that? We basically combine MAC with our encryption, right? So we not only encrypt something, but we also make sure that this encryption has not been modified, right? That somebody cannot change C with C prime and send that to the user. So there are two options. One is that the first, so let's say we have a message. We can first encrypt this message to get C, and then we compute the tag for C. We usually call this encrypt then MAC, okay? The other option is I first create the tag for the message, and then I'll encrypt the M and T and get the C, and then send the C. Okay, this is the second option. The second option is not a right way to do it. So you should not do first MAC and then encrypt. You always have to first encrypt and then MAC. So what I do is that I use, for example, AES or RSA or whatever other algorithm that I want for the encryption. I get my C, then I use the nested MAC or HMAC. So I use NMAC or HMAC to create the tag. And what I'm going to do is that I'm going to send the C and tag to the receiver. And this is what's called an AE or authentication encryption. It's guaranteed that it's going to be safe.
The tag is for the C, right?
Yeah, the tag is for this. Okay. So there are a few things remaining, including the digital signatures. So quickly, in the next lecture, I'm going to talk about those and then move on to the next topic, which is the malware. All right.